Hello everyone. Uh, this is the device lab. Here we are fabricating one MOS cap system, just like a MOS devices. So the entire class has been segregated in between the three classes, that is, which is depending upon our fabrication's entire lab procedure. So this is the first class. In this class, we have a demonstrating. We will show you up just the physical demonstration of the silicon wafer. On above of that, the MOS system has been developed, and another one is the very important issue is that the cleaning of the surface of silicon wafer. So what is actually the MOS system? That is metal oxide semiconductor. So the three step, that is, here we are using silicon wafer for our semiconductor system, for our semiconducting platform, and above of the silicon surface we will grow silicon oxide, which is the oxide part of this MOS system, and after that we will grow metal, that is actually we deposit metal over the silicon oxides, so which is the metal part of this MOS system. So metal oxide semiconductor. In these fashions, we will divide our lab classes between three different class. So the first class is the cleaning. After that is the class for the oxidations, and after that the class 3 will be the metallizations. Okay, so this first class is divided between the two parts. First one is the physical demonstration, that is the how many type of the wafer is there, what is the exactly wafer look like, what is the physical appearance the wafer will be, and the second part is the cleaning of the surface. So we will just move forward. First one is the different type of silicon wafer. The silicon wafer is made up of the single crystal silicon, and the process of making of the silicon wafer is called Rosalsky method or CZ process. Here's the first slide. The first picture, the showing you up the making of silicon wafer using the CZ process. That is, there is a large barrel which is contained molten polysilicon. There is no crystal orientation in between that, which is totally in the molten state. Another one, there is a large rod which is containing one seed crystal. So this rod is called ignat, which containing the seed crystal, which can go inside, which can go inside the molten silicon and comes out from the molten part, and when it comes out, so it's form a large solid barrel kind of thing outside of this seed crystal, and the controlling ignat rod is moving in a very different angle and with different speed, and according to that there is a different crystal orientation has been created in between that solid single crystal silicon rod, silicon barrel, whatever we said. And after that, after the formation of this crystal pooling, the large barrel kind of silicon rod has been shown in that figure 4. So it will be chopped off between a particular thickness, between a particular diameter, and according to the seed crystal presence, according to the seed crystal rotations, according to seed crystal angle variations, the diameter has been varied. So after the chopped up the entire bar, it can make a very thin slice silicon wafer we will get. So in that case, the silicon wafer, and after that the silicon wafer got polished, and after polishing it will be ready to make any type of devices above that silicon wafer. So on that note, silicon wafer is actually uh, segregated by four types of. First one is the type of doping, that is we have already known, that is the n-type doping, p-type doping, that is the intrinsic wafer is being doped by the extrinsic part. The second one is the amount, the type of crystal orientation is present inside of the wafer, that is the 1 1 plane or 1 0 0 plane is present inside the wafer. The 1 1 and 1 0 0 is the formation of the Miller indices. What is the Miller indices? We are all knowing that the Miller indices is the crystal plane cut is cut the axis, that is x y z whatever, and the portion of this integer inverse of that, creating a Miller indices. So the wafer can be 1 1 1 orientations, can be 1 0 0 orientations. Another type of the wafer is single side polished and double side polished, that is SSP and DSP. That means the silicon wafer is polished after the final formation and the device we will making above the polished surface. So when it is on single side polished, one side of the silicon wafer is polished just like a mirror like finish, another side of the silicon wafer is very opaque, not polished. But in case of double side polished, the both side of the silicon wafer is polished just like a mirror like. Another part is that the size of the wafer, that is the diameter, that is 1 inch wafer, 2 inch wafer, 3 inch wafer, 4 inch wafer. In our lab, actually we are using 2 inch wafer, sometimes it will be 4 inch wafer. The thickness of the 2 inch wafer is 275 micron. So this silicon wafer, we are using our semiconductor platform to make a MOS gap devices system. So now we are moving to the next slide, which here we are elaborating very. In this slide, we are elaborating the different types of wafer, that is P111 or N111, P100. But how can I visually distinguish in between two wafer? So the method is that a silicon wafer, if I take a silicon wafer, which is actually a rounded like structure, but it is not totally round, not circular kind of thing. There is a cut, that is straight line cut, which is clearly shown in the P type 111 wafer. In the bottom there is a line that is called cut. But in case of P100 wafer, there is another cut, which is in the less length than the another cut. That means there is actually a presence of two cut, which is the longer than the others. The longer one called primary cut, and which is the lesser than the others, the lesser one is called secondary cut. But the presence of primary and secondary and the angle between primary and secondary is the main method to distinguish any wafer, that is what type of crystal orientation is present on that. We can easily evaluate it. How can I that? So if we consider the first one, that is the P111 wafer, that is only the one cut is present in the below. But if we consider the P100, there is a primary and secondary cut. One cut is less than the other one, so the lesser one is the secondary cut, and the angle in between primary and secondary is called it is 90 degree in case of P100. But when it is the angle in between, that is 45 degree, it becomes N111 wafer. And similarly, when it is become 135 degree, it will be the 100. So if we visually check the presence of primary and secondary cut, and the angle between primary and secondary cut is actually helps us to determine what type of wafer you are using for our fabrications process. So in our lab or in our fabrication process, we are actually using P111 wafer or maybe P100. But why P111 wafer, I will discuss in the later. So now move to the most important part of this class, that is the cleaning process of the surface. That means if we take silicon wafer in a bare hands, or if we expose to in our ambience air or whatever, so the silicon wafer surface on that surface what you are planning to grow our MOS system. So it easily be contaminated and polluted by using any type of contaminations above the ambience and from our bare hands and anything. There's a huge chance of contaminations of organics, inorganics, particle, metal ions, dust, anything. So we have to clean the surface properly, so to make our devices in very good conditions, very defect free conditions. So this process is actually determined by what type of pollutants or contaminants stick over the surface. So the type of contaminants is mainly between two, that is organic pollutants and inorganic pollutants or metal ions. So in case of, if we there's a organic pollutants contents over that, the cleaning process is called acetone cleaning. But in case of organic and metal ion pollutants there's a two type of cleaning process, that is called RCA cleaning, another is called piranha acid cleaning. RCA, that is means Radio Corporation of America, they have a abbreviated form of that. This RCA cleaning is actually a basic cleaning, and piranha, that means already you have known the piranha fish, which it take out from all fleshes from our bones. So that this piranha cleaning process is actually acid cleaning. So in case of acetone cleaning, we are using the chemical actually acetone and DI water, nothing else. But in case of RCA, that is containing DI water, ammonium hydroxide, and hydrogen peroxides in a 5:1:1 ratio. But we are mainly focusing our piranha cleaning, as because of in our lab we will demonstrate this cleaning process for our P11 or P100, whatever wafer we have to clean the surface using that acid cleaning method, that is piranha cleaning. In this process we will require H2O2, hydrogen peroxides, and H2SO4 sulfur dioxide, hydrogen sulfuric acid in the ratio of 1:1 and 1:3. So this is the final slide, the final process. In our piranha cleaning process, the main two ingredients is 98% sulfuric acid and 30% hydrogen peroxide solutions. But the acid cleaning process is very much exothermic, so we have to very careful and have to be very take any precautions to run this chemical cleaning process. As because of that, we are using quartz beaker and quartz wafer holder. As because of that, if you using the glass vessel by borosilicate and kind of thing, this borosilicate glass cannot withstand the exothermic temperature, so we are using the quartz holder and quartz beaker. Wafer holder means we have to hold the wafer and put in the quartz beaker, and after that we are pouring H2O2 and H2SO4. So if you hold the silicon wafer, then we are using the Teflon tweezers, not any other tweezer that is SS kind of thing material. We are, for precaution, we are using nitrile gloves, and the borosilicate beaker here using just to hold the DI water. So you will just concentrating what the process is going on in this process. First we have to hold the silicon wafer using the holder and port of the quartz beaker, and then poured H2O2, that is hydrogen peroxides, first to that quartz beaker in a particular amount, and after that poured H2SO4, that is sulfuric acid, over that H2O2 on the same amount whatever you already poured on the H2O2, that is to maintain the 1:1 ratio. In case of industry, they are using 1:3 ratio for their requirement, but in our lab we are making 1:1. But it have to be reminded, I have to be keep your mind that we are first pouring H2O2 and then H2SO4, not the reverse. If we done in the reverse, then the huge exothermic explosion can be happened. So we are avoiding for that explosion. We are first pouring H2O2 and then H2SO4 in an equal ratio, and we have to keep the entire system just 40 to 45 minutes. There's a huge amount of bubble effervescence can come out for this cleaning process, and the huge amount of heat over there. And after 40 to 5 minutes, we have to the silicon wafer, whatever we are using, we have to take out from the solutions and rinse with the deionized water. Deionized water means we are not using any normal water, tap water. That means all normal tap water contain huge amount of metal ion contaminants. So this deionized water is totally cleaned and filtered, and maintaining its conductivity is very much high. That is 18.2 megaohm per centimeter. So this deionized water we are using for this cleaning process. And after the deionized water cleaning, we will show a significant change of the silicon wafer. That means the water got stuck over the surface in totally, but there is a chances of making of the native oxides. That means we don't want this native oxide, as because of that when we are exposing our silicon wafer to the ambience, in these conditions there is a huge chances of making of silicon oxide over the surface. But we are having a plan to grow our silicon oxides in a very defect free and uniform nature, so we have to remove or etch out this native oxide. So the next step, this wafer can poured again in the 1% buffer HF solutions to etch out the entire surface for this removal of native oxides. So poured again 1% buffer HF and then take out from the solution, and again we are rinsing with the DI water solutions. But remarkably that for the second time cleaning, we have clearly shown that no water got stuck over the silicon wafer surface. That means first, after the Piranha cleaning, the wafer is hydrophilic, and after the HF cleaning, the wafer is becoming hydrophobic. That means the changes between hydrophilic to hydrophobic is actually symbolizes that there is no native oxide present over the silicon wafer, and which is a visual examination process. That means we have etched out the entire native oxide layer over the surface. And after that we will dry out this wafer using the nitrogen gas, as because of this is an inert gas, using no other gases will be used. Flow using nitrogen gun, we have to flow over the surface, and this wafer can be stored in the desiccator, vacuum desiccator, that in the glass system. We have to store it over, and the entire air can suck out using the vacuum pump, and we have to store it up to the next classes. So here's the chemicals equation, that is H2SO4 and H2SO2, which gives the H2SO5, that is Carros acid, which is actually responsible for our cleaning process in the Piranha cleaning. Both two acids are very strong and reducing and oxidizing property. They can clean the entire surfaces. So there's a few precautions was there, just to not making any reverse directions of mixing. That is, first one is H2O2, then H2O4. We have to must use the quartz beaker and quartz wafer holder, that to avoid any type of explosions. There's the normal borosilicate glass cannot withhold this temperature, high temperature, and we have to use the nitrile gloves for the entire process, just to protect our hand. So this is the entire physical demonstrations of the silicon wafer and the surface cleaning process. And this cleaned wafer, we are moving to our next class. This is the oxidation process.